Let's understand the concepts chemical potential and thermodynamic activity in this video. These concepts are necessary in order to apply thermodynamics to open systems, in which exchange of matter happens between the system and the surrounding. For example, here matter gets added to the system. Now consider the two gases separated by a partition. If any one half is considered as the system, when the partition is removed, there is mixing of elements. If we are able to apply thermodynamic functions that we have derived in the video origin of thermodynamic functions to these open systems, we can understand and predict their behavior. Consider Gibbs energy function for this system. Let's say these blue atoms are atoms of component A, for example, a gas like argon. We know that it's a function of pressure and temperature. Now this is a closed system. If we make it an open system and consider addition of one atom to the system, the Gibbs energy is going to change. As the number of atoms increases, G is going to increase. Thus, it is also a function of number of atoms. In other words, it is an extensive quantity. It can be assumed to depend linearly on number of atoms, especially for small quantities. And the proportionality constant is mu A, and this is called the chemical potential of A. In fact, when the temperature and pressure are constant, the chemical potential can be defined like this. For an arbitrary component, change in Gibbs energy per atom of component I at constant pressure and temperature. A more practical definition involves number of moles of atoms instead of number of atoms, the small Na. Change in Gibbs energy per mole of component I at constant pressure and temperature. Consider gases A and B separated inside a container. The whole system has a certain Gibbs energy. When they mix, Gibbs energy of the system changes. In fact, Gibbs energy of component A and component B individually change, which is their chemical potential. Mu A, how much the Gibbs energy changes with respect to the amount of A at constant values of pressure and temperature and the amount of the other element B. Similarly, this is mu B. Gibbs energy change of the whole system is their weighted summation. All this may sound a bit vague now. Let's understand it in detail using some other way. First, let us be clear that the term mole fraction, which is one of the units for chemical composition, is actually a probability. Consider a solid, pure A, with its blue atoms sitting in their positions. Here only 30 atoms are considered for clarity. What is mole fraction of A? Number of A atoms divided by the total number of atoms. Since this is a single component system, both values are the same and the mole fraction is 1. This is actually a probability, isn't it? So whenever we come across mole fraction, this is what you should think about. It is the probability of finding an A atom at a particular atomic site. Now, consider this system. It's a solid solution of A and B called Phi. The orange colored ones are B atoms. Here the mole fraction of A is 30 divided by 60, which is 0.5. It means the probability of finding an A atom in an atomic site is 0.5, 50% chance. Let's say we have the pure A solid with 30 atoms. On top of it, consider a contained space with atmospheric air. All the usual air molecules and atoms are present. The pressure is 1 atmosphere. Among these atoms, there are 4 atoms of A. You may wonder, if A is solid at this temperature, how can there be vapor atoms of A, which would appear only beyond boiling point? In fact, vapor atoms do exist along with the solids in tiny amounts at almost all the temperatures. With increase in temperature, their count usually increases. Now, in the total pressure of 1 atmosphere, a part is due to these A vapor atoms. That is called partial pressure of A or vapor pressure of A. These atoms exist in equilibrium with the pure solid. Let's say solid is the standard state of pure A at this temperature. Now we are introducing one more new term, standard state. It means at atmospheric pressure, at this temperature, the temperature is below the melting point of A. The solid is the state. Here the partial pressure of A is called standard partial pressure, denoted by a superscript circle. Similarly, we can consider another solid B. 3 of its vapor atoms are exerting its standard partial vapor pressure. Fine. Now let's say these A and B atoms form a single solid solution phi. Let's say on top of it, the same number of A and B vapor atoms are present. If this is the case, then we can say this is ideal mixing between A and B, and the solid solution is called the ideal solid solution. Here A and B atoms do not interact. That is, an A atom does not bother whether the neighbor is A or B, meaning the bond energy and the equilibrium interatomic distance do not change if the neighbor of an A atom is another A or B. This is ideal mixing. As discussed in the video on meaning of enthalpy, the enthalpy change according to quasi-chemical theory is 0 in this case. Now, what about the partial pressure of A now? Before understanding it, let's have the mole fractions here. In pure A, the mole fraction of A is 1. In pure B, the mole fraction of B is 1. In the solid solution, since A and B atoms are equal in number, the mole fraction is 0.5 for both A and B. Let's figure out the partial pressure of A now. One thing is for sure, that on top of pure A solid, there are no B atoms, no orange atoms. But on top of this solid solution, there are B atoms. Therefore, a part of the total pressure is exerted by B atoms here. Therefore, the partial pressure of A on top of this solid solution is going to be less than that on top of pure A solid. In this ideal mixing case, the number of A atoms in the vapor state are exactly the same as those on top of pure A. Therefore, the standard partial pressure multiplied by the mole fraction of A in the solid solution is the partial pressure on top of the solid solution phi. Similarly, we can get partial pressure of B on top of phi. Now let's consider a different case. Here the vapor phase has only one blue atom, one orange atom on top of phi. That means the atoms prefer to stay in the solid state more. Why? Because there is an attraction between A and B in the solid state. They don't want to come easily to vapor state. It is fundamentally different from the ideal mixing case because A and B interact. This is called non-ideal mixing. This interaction is termed a negative interaction, in which an A atom prefers to have a B atom as the neighbor rather than another A atom. Here enthalpy change during mixing is negative. What about PA phi and PB phi? These values are less than mole fraction multiplied by the standard partial pressure of respective elements. Alright, Let's consider one more variation. Here the atoms in gaseous state on top of solid solution are more than those on top of pure elements. You could have sensed now that the A and B atoms tend to leave the solid state more. So A and B have repulsion, which also means they interact. This is also a non-ideal solution. Here it is called positive interaction. That is, an A atom tends to have another A atom as the neighbor rather than a B atom. And enthalpy change here is positive. What about Pa5 and Pb5? These values are more than the mole fraction multiplied by the standard partial pressure of respective elements. Now that we have understood what is mole fraction, vapor pressure, ideal and non-ideal mixing behavior, we are good to go for understanding what is activity. Let's consider the ideal mixing case again. No interaction between A and B. This ratio Pa5 to Pa standard, this is called the activity of A in phi, denoted with the letter small a. Substituting the expression for Pa5, we get this ratio to be equal to mole fraction of A. The formula gives a straightforward intuition for activity. Compared to its initial pure state, how active are A atoms in the final state of a solution? This intuition will become more appealing when we see the non-ideal solution cases shortly. In the ideal mixing case, the activity of A in the solution is the same as the content, the mole fraction of A in the solution. You can also imagine what will be the activity of A in pure A. There the initial and final states are the same, the pure A. So therefore the activity is Pa standard divided by Pa standard, which is 1. So activity of a pure element is 1. Now let's consider the non-ideal case with negative interaction. Here the ratio Pa5 to Pa standard is less than the mole fraction of A. So here activity of A is less than the mole fraction of A. It is similar for B as well. Intuitively we can see that the vapor atoms are lesser, meaning the A and B attract each other in the solid state, therefore they don't come easily to vapor state, meaning they are less active. The activity is low. The opposite is true in non-ideal mixing with positive interaction. The activity of A here is more than the mole fraction of A. Now, this is a good time to think about a scenario where with this solid phase phi, another solid phase is in equilibrium. Let's call it alpha. This new phase has a different mole fraction of A and B compared to phi. Although the total number of atoms are same, you can see alpha has more orange atoms than phi, and also atomic arrangement is different in alpha compared to phi. If these two phases are in equilibrium, activity of each element must be the same in both the phases, meaning the gas atoms above them must be in the same quantity. If that is the case, then there will be virtually no change. The two phases are in equilibrium. The entire two-phase system is stable. Otherwise, what will happen? These two phases cannot be in equilibrium. In that case, if enough energy is available, activation energy we call it, for the atoms to move, then there will be movement of atoms between the solid phases. That is called solid state diffusion. That will happen. The A and B atoms will be moving between alpha and phi, and their mole fraction in each phase will change. The diffusion happens as long as the activities of each element in both the phases becomes the same. Only then the two phases can stay in equilibrium. Fine. So activity of each element should be same in each phase. To summarize, for two or more phases to be in equilibrium, activity of each element must be same in each phase. Now we are in the right point to understand what is chemical potential. Think about these vapor atoms of A on top of pure A and on top of solid solution. The partial pressure values are the standard value and PA phi. Now we will understand what is the consequence of this change in pressure due to mixing from PA standard to PA phi. Let's start with considering Gibbs energy change of an ideal gas in a general pressure change situation, not from this PA standard to PA phi, some general pressure change. Let's call it some initial pressure to final pressure. Let's start with the expression we derived in the video origin of thermodynamic functions, dg equals vdp minus sdt. If we consider temperature to be constant in this pressure change, then dg will be equal to vdp, the sdt term disappears. If we consider the gas to be an ideal gas, then we can use the ideal gas law. dg is equal to nRT by p dp. If we simplify the calculation by considering 1 mole of gas as the system here, then dg is equal to RT by P dP. Let's say the general pressure change that we consider here is from P initial to P final. Integrating, we get a finite Gibbs energy change delta G, which is equal to RT natural log of PF divided by PI. Let's consider this final expression. Change the general pressure PI and PF to PA standard and PA phi to apply it to our mixing cases. Then we can get delta G A is equal to RT natural log of PA phi divided by PA standard. This is vapor pressure change during mixing of A from pure A to a solid solution phi. Now this ratio of pressure is nothing but activity of A in the solid solution. That's how we have defined activity. What we have done is by considering the behavior of vapor, we have derived the Gibbs energy change of the element A when it dissolves from pure state into a solid solution. Okay. So when we know the Gibbs energy change for a process, as we have seen in the video on Gibbs energy, we can talk about the feasibility of this mixing process itself according to the second law. So that is the power of this expression. In fact, this is only half of the story. We have to consider the B element as well. We'll do it shortly. What is the Gibbs energy change here? Let us write it in this way. Gibbs energy of A in the solution minus Gibbs energy of A in pure state, isn't it? We know that the solution also has B. Therefore, Gibbs energy of A in the solution can be called partial Gibbs energy. Sometimes a bar is used on top of G to indicate it. Also, a more standard way is to express this quantity per mole of A atoms. Therefore, the name partial molar Gibbs energy is used. This partial molar Gibbs energy is nothing but the chemical potential, mu A phi. We can write mu A phi minus mu A standard is equal to RT natural log of A, activity of A. Our chemical potential of A is equal to mu A standard plus RT ln of A. Similarly, we can derive mu B phi. The Gibbs energy of the solution is the weighted average of the partial molar Gibbs energy. Note one thing here. If you think about writing this mu phi instead of G of phi, it is not correct because chemical potential is defined only for each element in a phase and not for the entire phase. When it comes to the entire phase, we should talk only about Gibbs energy for the entire phase, not chemical potential of a phase. Chemical potential is always for an element. Fine. The Gibbs energy change of the phase depends on the chemical potential of both the elements. Recall that we started the derivation of mu A from VdP minus SDT. Therefore, for mu B, that is for the behavior of orange atoms, again the entire thing applies totally independently. Therefore, only VdP minus SDT is not going to give the total Gibbs energy change. P and T alone are not enough. Gibbs energy is a function of number of A and B atoms, or the number of moles of A and B atoms, isn't it? Which involves chemical potential. In subscript notation, we can represent it like this. Let's understand phase equilibria based on chemical potential. Chemical potential is a function of activity, fine. As we have just seen, for two or more phases to be in equilibrium, activity of each element must be same in each phase. Therefore, for two or more phases to be in equilibrium, chemical potential of each element must be same in each phase, isn't it? So this idea is extremely important to understand and predict phase equilibria in numerous scenarios. See you.